Polynomial inequalities with unusual solution sets. And we're going to see some unusual solution sets here. We start off, and actually we're going to be looking at two different expressions or functions where the only thing that really changes is the inequality itself. In this case, we've got x squared plus 2x plus 5 is greater than 0. And remember, if I graph this, I got to make sure I want that pointed end, the arrow end of that inequality facing the same way, which would be y is less than x squared plus 2x plus 5. And you can see I've got two regions here. I've got a region inside the parabola and I've got a region outside the parabola. And in this case, you can see that it's all shaded in, that the solution set is all outside of the parabola. And one way that if I didn't have the graphing calculator that would shade it for me, one thing I could do is I could set the origin, since I've got y equals 0 anyway, I could set the origin as my test point and see if that would give me a true statement. So if I substituted in 0 for x, well, x squared, 0 squared is 0, and 2 times 0 is 0, and so then I'm left with 5 is greater than 0, and is that true? And since that is true, I would shade towards the origin, just like you see what it has done. Now we might be asking, why don't we have any x-intercepts in this thing? Well, if I look at x squared plus 2x plus 5, two numbers that would multiply to 5 and add 2, well, 5 and 1 are the only two numbers, and there's no way I can get that to add to 2. So what would I end up doing? I'd end up using the quadratic formula of negative b, where b is 2, plus or minus the square root of b squared, or 2 squared, minus 4 times a, which is 1, times c, which is 5. And that's all over 2. And when I start solving inside the radical, well, I've got negative 2 plus or minus, 2 squared is 4, but negative 4 times 1 times 5 is negative 20, and 4 minus 20 is negative 16. And you can tell that that's not going to give me any real roots. That's going to give me imaginary roots. So therefore, in this case, what is our solution set? Well, if I look at the x-axis and think about it as a number line, every value of x is giving me, is part of my solution set. And so my solution set then, parentheses, because negative infinity goes out forever, and then infinity, parentheses, also goes out forever. And so my solution set then is negative infinity, positive infinity. Now let's look at this same equation or function, but this time we're going to see where it is less than or equal to 0. And again, I've already graphed it. I got the same two regions. I got outside the parabola, and inside the parabola. And again, if I didn't have the calculator to guide me here, I'd set this as a test point. I'd set x equal to 0. Y is already set to 0. And then I've got, is 5 less than or equal to 0? Of course, the answer to that is no. So I'm shading the region away on the opposite side of the origin in this case, since I use that as my test point. And again, the same reason is true. We're going to have imaginary roots. But what's my solution set? Well, I don't have any value of x that's in my solution set coming along the number line. And so my solution set, well, there's no solution. Now we're going to look at another equation, and we're also going to look at it two different ways. So here I got x squared minus 2x minus 15 is less than or equal to negative 16. Well, let's move this negative 16 over. And when I do, I've got x squared minus 2x plus 1. We'll set it as an equality for right now, but it's really less than 0. Well, let's see, what's the factor? Let's set two sets of parentheses because I can factor this. And I got an x without quadratic formula, and x. My constant 1 is positive. My middle term is negative, so it means I got two negatives inside the parentheses. Well, 1 times 1, and there it is. And so I've got two factors actually, and see, I can see that it's bouncing off right here at 1. And if I set each of those factors equal to 0, I'd come up with x equals 1, and that seems to make sense. But how do I determine my solution set? Well, there's only one, and let's see, this is a less than or equal to. So 1 is part of my solution because of the less than or equal to. And, well, Shazam here, my solution set is, and I'm using braces, 1, which means that 1 is included in my solution set. All right, let's look at this same thing, except this time we're going to say that it is greater than negative 16. And again, I'm going to pull the 16 over. My factors obviously would be the same. But what's happening here? And notice that I don't have an equal to, I've just got a simple greater than. And obviously, I'm shading away from, I'm shading the outside region, not the inside region of the parabola. Why would that be true? Well, if I use my test point here at 0, 0, for instance, if I didn't have the calculator and I was using a test point, is negative 15 greater than negative 16? And the answer to that is yes. And so I'd be shading towards, on the side, the region where the origin lies. Now, however, what is my solution? So I'm looking at all these values of x going down the x-axis, except that when I get to 1, because this is just a greater than, that's not included in my solution set. So then my solution set is this. I'm going all the way out to negative infinity, out in this direction, until I get to 1, and then I'm going to use a parentheses because parentheses is not included. It's not greater than or equal to, it's just greater than, and then it's in union with parentheses again, 1, up to 1, and then out to infinity, and Shazam, there we go. Now those were some unusual solution sets, weren't they? But it was a lot of fun.